Hello everyone. Today I will present my research on empirical evaluation of concurrency paradigms in Python for IO bound and CPU bound workloads. Python offers threading, multiprocessing, and asynchronous programming, but developers like clearly evidence on which model performs best. This study systematically benchmarks these paradigms under controlled conditions to provide data-driven recommendations for real-world Python application design. Introduction and background. Modern software systems demand high performance and scalability. Python is widely used in cloud computing and data intensive applications. However, the global interpret lock or GIL limits true parallel execution. Python supports three main concurrency models: threading, multipurposing, and each suited for different tasks. The problem is that developers lack empirical evidence to choose the right model. The research fills that gap. Problem statement and research questions. The core problem is this: although Python provides multiple concurrency options, there is no explicit practical evidence telling developers which model works best for CPU intensive versus IO intensive tasks. The GIL further complicates where this decision's current literature is disjointed. My premier research question asks, how do threading, multiprocessing, and stringing compare in performance for different workloads types in Python? Research aim and objectives. The main aim of this research is to empirically compare Python's concurrency models under constant hardware conditions. I have 5 specific objectives. First, design benchmark applications for both workload types. Second, measure key metrics like execution time and resource usage. And third, determine the GIL's effect on performance. Fourth, evaluate overheads and trades-off. And the last, fifth, formula practical evidence-based guidelines for Python developers selecting concurrency strategies. Literature review, concurrency and paradigms. Let me briefly review the three paradigms. Threading uses a shared memory model. It is a lightweight and good for IO tasks, but the GIL severely limits its CPU performance. Multiprocessing uses independent processes and each with its own memory and interpreter. This bypasses the GIL, enabling the true parallelism, but at the cost of the high memory overhead. Asynchronous is written driven using a single threaded event loop. It excels at thousands of concurrent IO operations. Literature gap and conceptual framework. Existing literature has a clear gap. Most studies examine each paradigm in isolation, not through a unified control comparison. There is no constant evaluation across the both workload types under identical conditions. My conceptual framework uses concurrency model and workload type has an independent variable with execution time, all through CPU throughput and memory has a dependent variables. This structure enables objective evidence-based recommendations for developers. Research methodology. I adopted a positive philosophy focusing on objective, measurable performance outcomes. The research design is experimental with controlled conditions, ensuring fair comparison across all 4 models. I used a dedicated approach, testing, executing, existing the theoretical assumptions with empirical data. The benchmarking framework was built in Python using Streamlit for interface and libraries like Pandas, Polyglot, Suite, and Signio for measurement and visualization. Benchmark implementation. I implemented 2 workload categories for CPU bound tasks. I used prime member computations and matrix multiplication to stress completion limits. For IO bound tasks, I simulated network latency using sleep operations. The measurement framework captured execution time using high Precocious timers CPU utilization with suit and memory usage with the trace malloc. Each experiment was repeated multiple times to ensure consistency and reduce variability in the results. Results CPU bound workloads. For CPU bound workloads, the results were clear. With lightweight prime counting, multiprocessing was actually slower due to process overhead, but with heavier matrix multiplication, multiprocessing emerged as a winner, achieving about 22% faster execution than sequence. Threading showed only 10 marginal improvement around 10% because the GEL prevents true parallel execution of Python bytecode. A new performance similarly to sequential as expected. Results. The IO bound results showed a completely different pattern. The sequential baseline took about 2 seconds for 20 simulated tasks. Both threading and achieved approximately 0.1 seconds, that is 19-fold speed up. They effectively overlapped. The comparative analytics confirms that the GEL is the deciding factor for CPU bound matrix multiplication. Processing is the best for IO bound tasks. Threading are the best. Multiprocessing is worst for IO due to overhead, while threading is worst for CPU due to GEL speed up. Factors range from 1.24 times for CPU tasks, but 10 to 20 times for IO tasks. Choose based on your overload type. Resource usage also varied significantly for CPU-bound workloads. All models show near 100% CPU utilization, but multiprocessing used for more memory due to process isolation. For IO-bound workloads, CPU usage was very near to zero across all models because tasks spent time waiting, not computing. A scenario showed the most constant execution times with low variability, making it ideal for predictable and high concurrency IO applications. So, what are the practical takeaways? There is no one size fits all solution for heavy computation like data science or machine learning. Use multiprocessing to bypass the alpha high concurrency IO like web servers or API clients. Use Sensio for its low overhead and massive scalability. For moderate IO with simpler code, threading works well. For mixed workloads, consider a hybrid approach, combining multiprocessing for CPU pods and Sensio for IO pods. This study empirically confirms the theoretical impacts of GL in Python. Multiprocessing is best for CPU-bound work. Sensio is best for IO-bound high concurrency work. Threading is a viable alternative for IO but fails for CPU work. However, limitation exists. I used simulated IO workloads which may not reflect real network behavior. Testing was done one single hardware configuration. I used descriptive rather than statistics. And this is my reference. And thank you so much for your time and attention. This research was conducted with goal of providing clear and empirical guidance for Python concurrency decisions. Thank you to all who contributed to support this study.